when the internet finds the water plant, how exposed industrial controllers are turning America's smallest utilities into targets in a much larger cyber conflict, by Jonathan Brown. On July 30, the Federal Bureau of Investigation and Environmental Protection Agency issued a warning remarkable for the ordinariness of the technology involved. Since July 27, water and wastewater utilities in at least 7 states had reported cyber incidents involving internet-facing programmable logic controllers. The devices were Rockwell Automation/Allen Bradley Micrologic's 1100 and 1400 PLCs, small industrial computers commonly used to monitor and control physical equipment. Attackers were remotely accessing them, changing their IP addresses and passwords, and causing operators to lose monitoring and control. Some incidents degraded water operations. One organization found altered PLC project files after discovering discrepancies in ladder logic across several sites. Reported effects included loss of water pressure and flooding. That ought to stop anyone who still thinks of a cyber attack as something that happens principally to information. A compromised email server may expose correspondence. A compromised accounting system may expose money. A compromised PLC may affect whatever machinery has been wired to its outputs. A pump does not know that the command telling it to stop originated from an Iranian intelligence service, an ideologically motivated hacker, a criminal, a teenager experimenting with an industrial protocol, or an authorized engineer. The pump knows only that the controller instructed it to stop. This is where cybersecurity becomes infrastructure security, and the events of 2026 suggest that the boundary between the two is becoming dangerously thin. There are actually 2 related but analytically distinct stories unfolding in American water infrastructure, and they should not be carelessly combined. The first is an attributed campaign. The FBI, CISA, NSA, EPA, Department of Energy, U.S. Cyber Command and Treasury have warned that Iranian-affiliated advanced persistent threat actors are actively targeting internet-connected PLCs across American critical infrastructure, including water and wastewater, government facilities, and energy. The campaign has affected equipment from Rockwell Automation, Schneider Electric, and Siemens, and has involved theft and modification of PLC project files, manipulation of HMI and SCADA displays, disruption of controller functions, and in some cases, operational disruption and financial loss. The government assesses that the Iranian-affiliated group is conducting the activity with the intention of causing disruptive effects inside the United States. The second is the wave disclosed on July 30 involving Micrologic's 1100 and 1400 controllers at water utilities in at least 7 states. The FBI and EPA described those attackers simply as malicious cyber actors. They did not attribute that specific set of incidents to Iran. Minnesota, where operational technology at more than 30 community water systems was targeted on July 26 and 27, has likewise explicitly said that it has not attributed the activity to a specific actor and has not determined that every incident was necessarily performed by the same actor. That distinction is not a nuisance to the story, it is part of the story. Because whether the latest attacks eventually prove Iranian, criminal, hacktivist, or something else, both campaigns expose the same structural weakness. Industrial computers capable of affecting physical processes are reachable from a global network, populated by people who should never be able to talk to them. And once that is true, the attacker does not necessarily have to find the water plant. The internet can find it for him, the little computer that runs the physical world. A programmable logic controller is essentially a purpose-built industrial computer designed to perform controlled tasks reliably for long periods in environments where ordinary desktop computers would be inappropriate. A PLC repeatedly reads its inputs, evaluates programmed logic, and updates its outputs. The inputs may represent pressure switches, flow meters, tank levels, temperatures, motor states, or other process measurements. Outputs can operate pumps, valves, relays, motors, alarms, and other equipment. In a water system, one PLC might monitor the level of an elevated storage tank and activate a pump when the level drops below a specified threshold. Another might monitor pressure in a distribution zone. Another could operate wastewater lift station pumps. Yet another could participate in filtration, chemical treatment, or other process functions. The important point is not that every PLC performs a life or death function. Many do nothing particularly dramatic. The point is that software decisions inside the controller are translated into physical actions outside it. Rockwell's MicroLogix family illustrates the convergence particularly well. The MicroLogix 1400 builds upon the MicroLogix 1100's networking capabilities and includes Ethernet connectivity, Ethernet IP support, embedded web functionality and support for industrial communications, including DNP3. The 1100 is now discontinued, although it remains installed in operational environments. Rockwell recommends migration toward its newer Micro 800 platform. These were useful features. They made industrial automation easier to integrate, monitor, and maintain. They also meant that a device designed to operate machinery could communicate across modern networks. That is not itself a design failure. Industrial systems need communications. Remote pumping stations may be miles from the treatment plant. Water towers, wells, lift stations, and other equipment may be geographically dispersed. Utilities benefit enormously from being able to monitor equipment remotely rather than dispatching an employee every time somebody wants to know a tank level. The security failure occurs when remote connectivity becomes direct public reachability. Rockwell's own March 2026 security guidance could hardly be clearer. Controllers should not be exposed directly to the public internet. Unauthenticated open ports should be closed at the edge, controller security protections should be enabled, and OT networks should employ defense in depth and segmentation. Yet the federal government is now responding to exactly the condition Rockwell says should not exist. PLCs are on the internet, and attackers are reaching them. What loss of view actually means. The phrase appearing repeatedly in federal industrial security advisories is loss of view. It sounds almost benign. It isn't necessarily. Industrial processes depend heavily on the operator's ability to understand what the process is doing. That understanding usually comes through a human-machine interface, or HMI, and in larger systems through supervisory control and data acquisition, or SCADA. The HMI turns process variables into something useful to a human being. A screen may show a reservoir level, pump status, valve position, pressure, flow, or alarm condition. Instead of reading raw electrical signals, the operator sees a graphical representation of the plant. That representation is part of the control system. If the physical process changes and the operator can see it, the operator may intervene. If the operator's view is lost, intervention becomes slower and more difficult. If the displayed information itself is falsified, the problem becomes considerably more dangerous. The human being responsible for correcting the process may be making decisions from an incorrect representation of reality. The Iranian-affiliated campaign has crossed precisely this boundary. Federal agencies say the actors have maliciously interacted with PLC project files and manipulated information displayed on HMI and SCADA systems. Investigators also found modification and deletion of PLC logic, including reusable add-on instructions and changes that disabled critical shutdown and alarm logic, potentially allowing an industrial process to enter unsafe conditions without warning the operator. This yields two distinct forms of integrity that industrial defenders have to protect. The first is process integrity. Is the controller actually running the correct program? The second is observational integrity. Is what the operator sees an accurate representation of what the process is doing? An organization that answers only one of those questions has not established the trustworthiness of the system. Ladder logic is not merely code. PLCs can be programmed in several ways, but one of the best-known industrial programming forms is ladder logic. The name comes from its visual appearance. Programs are represented as horizontal rungs between vertical rails, resembling an electrical relay ladder diagram. Conditions are evaluated and outputs activated according to relationships expressed in those rungs. An oversimplified pump control program might amount conceptually to this. If the tank level is low, the pump is available, no safety interlock is active, and the system is in automatic mode, run the pump. Real programs can be vastly more complicated. They incorporate timers, counters, analog values, reusable instructions, alarms, permissives, shutdown conditions, sequencing and interaction with other controllers. But the crucial characteristic is that the program embodies operational intent. It tells the machine what the operators and engineers have decided is supposed to happen. Change that logic and you have changed the plant's rules. The July 22 update to the Iranian-affiliated PLC advisory contains one of the most consequential technical details yet publicly disclosed about the campaign. At one U.S. victim, the FBI observed the actors downloading a malicious project file into a PLC with ordinary configuration software. Analysis found that the replacement file retained the ladder logic necessary for downstream functionality, but added logic overriding particular instructions responsible for maintaining safe operating parameters. That is a much more sophisticated effect than simply crashing a controller. The machinery can continue to function, the program can still look substantially like the real program. But somewhere inside it, assumptions upon which safe operation depends have changed. The attacker has not necessarily destroyed the process, he has altered its laws. And the attacker may not need malware. This is one of the most important lessons in modern operational technology defense. Much of cybersecurity trains us to look for malicious executables. Industrial systems complicate that model because legitimate engineering software already possesses extraordinarily powerful capabilities. Engineers must be able to upload PLC programs. They must be able to download programs. They must change parameters. They must diagnose equipment. They must inspect logic. They must place controllers in different operating modes. They must sometimes modify a process while the plant is running. A threat actor who obtains equivalent authority may not require a custom malware framework because the vendor's own engineering environment already performs the required operations. Federal investigators observed Iranian-affiliated actors using Rockwell Automation Studio 5000 Logix Designer, Schneider Electric Eco Structure Control Expert, and Siemens Totally Integrated Automation Portal from leased third-party infrastructure to obtain project files from victim PLCs. The targeted devices included Rockwell Compact Logix and Micro 850 controllers, Schneider Modican M340 PLCs, and Siemens S7 1200 controllers. The maliciousness is therefore not necessarily contained in the software. It is contained in who possesses authority to use it. This is why an industrial attack can be difficult to distinguish from maintenance when viewed only at the protocol level. A legitimate engineer may connect to a controller and download a project file. An attacker may connect to the same controller and download a project file. The industrial protocol sees two valid operations. The defender has to determine whether the person or machine behind the operation had legitimate reason to perform it. Security at this level is about controlling authority, not merely detecting malformed packets. The internet changes who gets to choose the target. Historically, attacking an industrial process required some knowledge of where that process existed. You needed to know the facility. You needed physical proximity or some pathway into its communications. You needed to understand enough of the technology to identify the equipment. Internet exposure reverses that sequence. The attacker can begin with the equipment. The Federal Iranian Advisory describes actors using foreign IP addresses and leased hosting infrastructure to reach internet-facing PLCs. Malicious traffic was observed against ports associated with Rockwell, Schneider and Siemens industrial communications, as well as SSH on modems. The agency's conclusion from the breadth of protocol targeting is important. The actors appear to be opportunistically searching across manufacturers, not limiting themselves to one vendor's equipment. Imagine what that means conceptually. The attacker does not necessarily begin with, find the controller operating the municipal water plant in this town. He can begin with, find controllers of this family that answer from the internet. Only after discovering the device does he determine what organization owns it and what physical process it operates. This is infrastructure discovery at internet scale. The targeting economics are radically different. Reconnaissance that once required travel, insiders, engineering knowledge, or patient investigation can increasingly begin as a search problem. The vulnerability can effectively select the victim. And that is an especially dangerous development for small infrastructure operators because obscurity is no longer meaningful protection when the device itself can announce its existence to the network. Minnesota demonstrates the multiplication effect. The Minnesota incidents illustrate what happens when a repeatable attack path meets a decentralized utility sector. On July 26 and 27, malicious cyber activity targeted operational technology at more than 30 Minnesota community water systems. Minnesota IT Services activated a statewide response involving state agencies, local utilities, CISA, EPA, the FBI, and other partners. 2 days later, the state clarified what affected meant. Most confirmed cases involved technology used to remotely monitor and control water equipment, including PLCs and HMIs. Minnesota emphasized that confirmed malicious activity against the technology did not mean every affected community experienced interruption to water service. The state also explicitly declined to attribute the incidents and said investigators had not established that all of them were performed by one actor. Those qualifications matter. No responsible analyst should turn 30 affected systems into 30 towns lost drinking water. They did not, but the absence of catastrophe should not conceal the extraordinary fact underneath the incident. Someone was able to touch the operational technology of more than 30 community water systems during a coordinated episode spanning roughly 2 days. That is scale. It does not require a cyberweapon capable of penetrating 30 completely different architectures if those architectures share the same exposure pattern, the same integrator configuration, the same remote access mechanism, or the same family of devices. The FBI's July 30 warning makes this possibility explicit. Investigators found similarities in network setups provided by third parties across multiple victims and warned that shared vulnerable hardware and network configurations can allow attackers to multiply a successful method across customers. This is the supply chain problem in a form that receives less attention. The supplier does not have to distribute malware. An integrator can unintentionally distribute architecture. If 20 utilities use essentially the same remote access design, the attacker who learns how to defeat one may have learned something about 19 others. Standardization is usually good engineering. Standardized insecurity is something else. Small utilities are still critical infrastructure. American water infrastructure creates a particularly difficult defensive problem because it is highly decentralized. A large metropolitan utility may have dedicated network engineers, security personnel, sophisticated segmentation, and round-the-clock operations. A small community utility may have a handful of employees, contracted IT support, aging industrial equipment, and operators whose primary expertise is water, not adversary emulation, firewall engineering, or threat hunting. EPA acknowledges this problem directly. Its National Water Program Planning has noted that many water and wastewater utilities, particularly small systems, lack the resources for dedicated information technology and security specialists. Federal law itself reflects a resource and scale boundary. Safe Drinking Water Act Section 1433 requires community water systems serving more than 3,300 people to conduct risk and resilience assessments and develop emergency response plans. Systems serving 3,300 or fewer are not subject to that particular RRA requirement. Yet the PLC does not care whether it serves 2,900 people or 29 million. Neither does the attacker. A small town can still have elevated tanks that require pumping. It still has pressure zones. It still has wastewater that must be moved. It still has treatment systems. It still has customers who expect water when they open the faucet. This produces one of the central asymmetries in American critical infrastructure defense. National infrastructure is partly composed of organizations that individually possess local government-scale resources while facing internet-scale adversaries. The attacker scales cheaply. The defender frequently cannot. The government has been warning about this for years. None of this arrived without warning. EPA's cybersecurity enforcement alert states that cyberattacks against community water systems have been increasing in frequency and severity, and that actual incidents demonstrate the possibility of manipulating operational technology. EPA identifies potential consequences including interruption of treatment, distribution and water storage, damage to pumps and valves, and improper chemical levels. More revealingly, EPA reported that more than 70% of systems it had inspected since September 2023 were violating basic requirements associated with risk, and emergency planning. Inspectors encountered elementary security failures, including unchanged default passwords, shared staff accounts, and access that had not been revoked for former employees. Those findings are worth considering beside the extraordinary sophistication often attributed to nation-state cyber operations. There are places where America faces very advanced adversaries. There are also places where the adversary may not need to be advanced. If the controller is directly exposed to the internet, if the password is weak, if remote access bypasses a monitored gateway, or if an obsolete device is still trusted because replacing it would require an expensive engineering project, the adversary can spend its sophistication elsewhere. Sometimes the attacker's most powerful exploit is simply the defender's architecture. Iran learned this lesson years ago. The current Iranian-affiliated campaign has an important predecessor. Beginning in November 2023, the IRGC Cyber Electronic Command-affiliated group, commonly called Cyber AV3 Ingers, targeted US PLCs and HMIs, including Unitronics devices used in water and wastewater facilities and other critical infrastructure environments. The 2026 Federal Advisory now says that campaign compromised at least 75 devices. The actors developed malicious ladder logic and replaced legitimate PLC logic with their own code. The government says the malicious code from that campaign continues to be observed. The importance of the history is not that the present Micrologic's attacks must therefore be Iranian. Again, they have not been publicly attributed. The importance is that US adversaries have already demonstrated that they understand the strategic value of Internet-exposed industrial control equipment. Once a nation-state discovers that a class of American infrastructure can be reached directly, we should assume that lesson will not be forgotten. The 2026 Iranian campaign has broadened beyond Unitronics. Federal agencies now describe targeting of Rockwell Automation, Schneider Electric and Siemens systems, potentially alongside other manufacturers. The actors have progressed from accessing exposed equipment to removing project files, modifying logic, changing what operators see, and disabling alarm and shutdown functions. This looks less like fascination with one Israeli-branded controller and more like the development of a general capability. Find exposed industrial equipment, learn the environment, acquire the engineering project, alter process behavior, and create disruption. That is a doctrine. Pressure loss sounds mundane until you understand water systems. One of the operational consequences reported in the July 30 FBI EPA warning was loss of pressure. Another was flooding. Water pressure is not merely about whether the shower works. A pressurized drinking water distribution system is designed in part to keep external contamination outside the pipe. Significant pressure loss can create conditions under which groundwater or other contaminants can enter through cracks, joints, or damaged infrastructure. The FBI and EPA specifically warn that pressure loss may allow untreated groundwater to seep into piping. That illustrates an important feature of cyberphysical systems. The attacker does not necessarily have to perform the final harmful act directly. He may only need to alter the conditions under which ordinary physics creates the consequence. Stop a pump, change a pressure setpoint, prevent an operator from seeing the state of equipment, disable an alarm, modify logic controlling a valve. The ultimate effect emerges from the plant. This is what makes OT compromise fundamentally different from many enterprise attacks. The computer is not merely storing a representation of reality, it is participating in the creation of reality. Manual operation is an independent control plane. The July incidents also contain a lesson that appears almost technologically backward until one understands its importance. The FBI and EPA repeatedly emphasize the ability to switch to manual operations. The agencies state that the ultimate operational effect of the July incidents depended partly on what function the PLC performed and whether the utility could revert to manual operation. They explicitly recommend that water systems maintain and exercise manual controls, fail-safe mechanisms, islanding capabilities, backups, and standby systems. This is not nostalgia for an analog past. Manual operation is redundancy. More precisely, it can be an independent control plane. If the network becomes untrustworthy, somebody can go to the pump station. If the remote HMI disappears, an operator can inspect physical instrumentation. If automation fails, procedures can sustain essential service while engineers reconstruct the controller. That independence matters because resilient systems require some recovery mechanism that does not depend entirely on the thing that has failed. A backup joined to the same compromised administrative domain is not fully independent. A redundant HMI connected through the same vulnerable network is not fully independent. A second remote controller exposed through the same modem is not fully independent. A human operator with a local control mechanism may be. The appropriate level of manual capability will differ radically among plants, and manual intervention itself can carry safety risk. But the principle is powerful. Cyber resilience sometimes requires deliberately preserving a way to operate without cyberspace. The physical mode switch may be a cybersecurity control. There is another beautifully simple defensive mechanism in the federal recommendations, the controller's mode switch. Where supported, agencies advise operators to place the PLC's physical or software key switch into run mode after programming is complete so that remote modification of logic, configuration or firmware is blocked or restricted. Controllers should enter program or remote modes only when legitimate engineering work requires it, and should be returned to run afterward. Think about what that means. An advanced threat actor can own servers in foreign data centers. It can possess the vendor's engineering software. It may know the device's address. It may understand the protocol. It may have credentials. And a physical switch in a locked cabinet can still deny one of the most dangerous actions, that is defense in depth in its purest form. The security control succeeds because it lives in a different domain from the attack. The network does not get a vote. This is why cyber-physical defense cannot consist solely of more cybersecurity software. Physical controls, operating procedures, independent safety systems, engineering interlocks, mode restrictions and manual capabilities can all constrain what stolen digital authority is allowed to accomplish. But the switch creates a recovery problem of its own. The FBI's guidance contains an important warning that illustrates how carefully OT response has to be handled. Before placing a controller into run mode, operators are told to review and validate the project file, because switching modes may effectively lock in whatever project has already been downloaded. If an attacker has already modified the program, protecting that program against further modification does not restore integrity. It preserves the malicious state. This is why patching, password changes and network isolation do not automatically close an industrial incident. After credible PLC compromise, defenders may have to determine: is this the correct project? Is the ladder logic identical to the engineering baseline? Were reusable instructions changed? Are input-output mappings correct? Were alarm thresholds altered? Were shutdown instructions removed? Does the HMI display the real process variables? Can the engineering workstation be trusted? Was the cellular modem compromised? Are the backups older than the intrusion? Could the backup itself contain the modified logic? The FBI and EPA specifically instruct organizations to compare running PLC programs against known good logic, validate reusable code and I/O configurations, examine connected modems, HMIs and workstations for lateral activity and verify that backups do not contain malicious logic before restoring them. In Enterprise we often talk about restoring files. In OT, defenders may have to restore engineering truth. The cellular modem matters as much as the PLC. Remote industrial equipment is frequently connected over cellular infrastructure because running dedicated communications to every well, tower, pumping station or lift station may be impractical. That means the actual edge of the OT network may not be a sophisticated firewall in the treatment plant. It may be a modem in a cabinet at a remote site. Federal investigators have observed Iranian-affiliated attackers targeting modems over SSH, and in one instance using drop-bear SSH on a victim modem to facilitate remote access. The July federal guidance therefore tells utilities to secure cellular modems with strong authentication, update them, enable logging and consider more isolated architectures such as private APNs, site-to-site VPNs, and other controlled connectivity models. This is another reason a simple asset inventory becomes a national security control. The organization has to know that the modem exists, who owns it, who pays for the SIM, who knows its password, Does the utility manage it, or does an integrator? Does it accept inbound connections? Who can administer it? Is logging enabled? What sits behind it? When was its firmware last updated? What happens if it is disconnected? A network diagram that stops at the treatment plant firewall is useless if a second path enters through cellular equipment at a remote station. Attackers do not respect the architecture printed in the compliance binder. They use the architecture that actually exists. Third-party convenience can become shared exposure. One of the most important sentences in the FBI's July 30 alert may be the least dramatic. Investigators observed that similarities in victim network arrangements provided by third parties could allow malicious actors to multiply successful attacks when customers share vulnerable configurations and hardware. This deserves much more attention. Small utilities frequently rely on integrators because specialized industrial automation expertise is expensive and uncommon. The integrator designs the control panel. The integrator programs the PLC. The integrator configures remote access. The integrator may provide long-term maintenance. That arrangement can be entirely reasonable, but if remote maintenance architecture is replicated across clients, the integrator has indirectly created a common security assumption. Perhaps every customer receives a similar cellular gateway. Perhaps the same firewall rule is reused. Perhaps the same remote access model is deployed everywhere. Perhaps there is insufficient isolation between the public network and the PLC. An attacker who discovers the pattern at one customer may then recognize it at another. This is not necessarily a conventional supply chain compromise. No vendor has to be hacked. No poisoned software update needs to be distributed. The supply chain can propagate weak configuration. That means utilities need to treat architecture supplied by integrators with the same seriousness they apply to equipment supplied by manufacturers. What did you install? Is no longer enough. The better question is, what trust relationship did you create? The defensive answer is not mysterious. Despite the seriousness of the campaign, the first defensive actions are almost embarrassingly straightforward. Disconnect PLCs from direct internet exposure. Rockwell says it, the FBI says it, EPA says it, CISA says it. The July 30 advisory recommends placing remote access behind a secure gateway or jump host so that external access is brokered, authenticated, monitored, and controlled rather than terminating directly on the industrial controller. Network access should then be explicit. A PLC does not need to communicate with the internet. It needs to communicate with particular devices performing particular functions. Firewall rules and access control lists can therefore be designed around expected industrial relationships. This HMI talks to this controller. This engineering workstation can reach this programming service. This historian receives this processed data. Everything else is unnecessary until somebody demonstrates otherwise. External access should use strong authentication, with MFA implemented at the VPN, gateway, or higher-level access layer when the controller itself cannot support it. Cellular gateways should be hardened and logged. Default credentials should disappear. End-of-life equipment should be replaced where practical or isolated behind compensating controls where replacement cannot occur immediately. None of that sounds futuristic. That is precisely what makes the situation so disturbing. The United States does not need to invent a quantum-resistant, artificial intelligence-enabled industrial defense system before it can materially reduce this threat. Much of the immediate problem can be reduced by stopping the public internet from speaking directly to the machine that runs the pump. But remediation is not merely put a firewall in front of it. There is a danger in making the solution sound too easy. Some of these systems have been operating for years. Documentation may be incomplete. The engineer who designed the original architecture may be gone. A vendor may need remote access for maintenance. The PLC may be part of an obsolete but operationally essential system. Moving it behind a different network architecture may interrupt communications upon which the plant depends. Firmware updates can require process downtime. Replacing an old controller may require rewriting logic, retesting I/O, modifying panels, validating instrumentation, and conducting commissioning work. Industrial security changes therefore have to be made with operational engineering discipline. The risk is not simply that somebody fails to secure the device. The risk is also that a defender, responding hurriedly to an advisory, accidentally removes a control path required to operate the plant safely. That is why the correct phrase is not just disconnected. It is remove unsafe public exposure while preserving a tested, controlled mechanism for legitimate operational access. Those are different things. The real vulnerability is the assumption of a trusted world. Industrial control systems were built around a very different historical assumption from modern internet services. A traditional industrial network often operated inside a plant. The people who could reach the PLC were presumed to be engineers or operators. The network itself therefore carried an implicit element of trust. That design made sense when reaching the protocol required standing inside the facility or connecting to a private industrial network. The internet destroys that assumption. An industrial protocol that is entirely acceptable inside a trusted plant can become dangerous when exposed globally, because the device may not possess the defensive layers expected of a modern public-facing server. We should therefore be cautious about calling every incident a PLC vulnerability. Sometimes the controller is performing exactly as designed. It receives an engineering connection. It accepts a configuration command. It loads a project. It changes a parameter. The vulnerability exists one level higher. Someone gave the entire internet a path to ask. This is why attribution is secondary to architecture. We should eventually learn who conducted the July attacks. If Iran was responsible, that matters. If a criminal group was responsible, that matters. If an ideological hacktivist collective was responsible, that matters. Attribution affects geopolitical response, intelligence collection, law enforcement, and our understanding of the adversary's intentions. But attribution does not alter the underlying engineering failure. A publicly exposed PLC does not become safe when the attacker turns out not to be Iranian. Nor does an insecure remote access architecture become acceptable because this weak scanning came from criminals rather than a military intelligence service. The architecture determines who can reach the process. Attribution tells us who did. Infrastructure defense has to solve the first problem before intelligence analysts finish solving the second. Minnesota's restraint is therefore instructive. Officials have said the timing and technology involved show similarities among incidents, but they have not concluded that every incident involved the same perpetrator. They are allowing forensic evidence to lead attribution rather than fitting evidence to geopolitical expectations. That is exactly how critical infrastructure intelligence should work. A larger threshold has been crossed. The most consequential fact about these incidents may be the change they represent in the economics of physical disruption. It is expensive to build a water system. It is expensive to operate one. It requires pumps, tanks, treatment equipment, piping, instrumentation, laboratories, trained operators, electrical power, chemicals, maintenance, vehicles, regulatory compliance, and decades of accumulated engineering knowledge. It can be very inexpensive to send a packet. That asymmetry creates leverage. The attacker may spend dollars on rented infrastructure. The defender may spend days sending engineers across a region to inspect and reconfigure remote sites. The attacker changes a password in seconds. The utility loses remote visibility until somebody reaches the equipment. The attacker modifies logic. The utility has to locate the authoritative engineering backup, compare programs, validate interlocks, and determine whether the process can safely return to automatic control. The attacker's action is digital. The defender's recovery may be physical. That is a remarkable strategic return. And it explains why small infrastructure systems increasingly deserve the same national security attention once reserved for giant utilities. 30 small water systems are not 30 irrelevant targets. They are 30 pieces of American critical infrastructure. The most important backup may be knowing what correct looks like. Every utility should possess backups, but the 2026 campaigns suggest a more demanding requirement. Organizations need known good engineering baselines. The question after compromise is not simply whether a project file exists. It is whether the organization can prove that the file represents the intended process. That means preserving controller programs, configuration, firmware information, network settings, reusable logic, HMI projects, and other relevant engineering artifacts in a manner that allows comparison after an incident. It means controlling who can change them. It means documenting authorized modifications. It means having enough engineering knowledge available during incident response to distinguish a legitimate rung-of-ladder logic from an attacker-added override. Because if the attacker has been inside the controller, restore the latest backup is no longer a sufficient instruction. What if the latest backup was created after compromise? What if malicious logic was faithfully backed up? What if an engineer later modified the legitimate project but failed to archive it? What if the PLC contains a program that no longer matches the copy on the engineering workstation? Backups preserve bytes. Resilience requires preserving truth. The water plant on the public internet is a warning about everything else. Water is the immediate story, because that is where operational disruptions are being publicly documented. But the architectural lesson extends far beyond water. PLCs operate factories, they run portions of energy systems, they control building infrastructure, they operate conveyors. They interface with pumps, valves, compressors, and motors across industrial sectors. The Federal Iranian Advisory itself spans water and wastewater, government facilities and energy, and investigators have observed targeting across multiple manufacturers precisely because these technologies are broadly deployed. The same principle extends to other operational technology: remote terminal units, HMIs, engineering workstations, building management controllers, automatic tank gauges, industrial gateways, and network equipment connecting remote sites. Any device that converts digital authority into physical consequence deserves scrutiny when it becomes externally reachable. The question should therefore not be, why would Iran want our water plant? That is too narrow. The more useful question is, why can somebody on the other side of the planet reach the computer controlling our physical process at all? When the internet finds the water plant, for most Americans the water system is effectively invisible. You turn a handle, water appears. Behind that act lies an enormous physical and institutional machine. Wells, reservoirs, rivers, treatment processes, chemical systems, pumps, tanks, pipes, laboratories, maintenance crews, operators, regulators, and increasingly a layer of industrial computing that makes the system observable and controllable across distance. That computing layer provided enormous operational advantages. It also created a new kind of border. And in too many places, that border was never built as though hostile intelligence services, ideological hackers, and opportunistic criminals would one day be standing immediately outside it. Now they are. The FBI says attackers have reached water sector PLCs in at least 7 states and caused pressure loss, flooding, and loss of monitoring and control. Minnesota says operational technology at more than 30 community water systems was targeted in one coordinated episode. Federal agencies say Iranian-affiliated operators have been targeting internet-exposed PLCs across U.S. critical infrastructure since at least March, stealing project files, modifying logic, manipulating operator displays, and disabling shutdown and alarm functions. The same agencies say an earlier IRGC-affiliated campaign compromised at least 75 American PLC HMI devices. Rockwell says its controllers should never be directly exposed to the public internet. EPA says water systems continue to exhibit basic security weaknesses and that small utilities are not immune from cyber attack. None of these facts requires exaggeration. They are disturbing enough exactly as they are. The United States has spent decades connecting physical infrastructure because connectivity made infrastructure more efficient. Now comes the second half of the engineering project, making sure connectivity does not quietly transfer operational authority to anyone who discovers the endpoint. That requires better networks, better authentication, better inventories, and better segmentation. It requires treating cellular modems and engineering workstations as part of the plant rather than peripheral conveniences. It requires knowing what project file belongs in every controller. It requires preserving manual operations where they provide genuinely independent resilience. It requires modernizing equipment whose age has turned it into permanent technical debt. It requires scrutinizing the architectures supplied by integrators. And above all, it requires abandoning one disastrously obsolete assumption. That because an industrial computer is located in a locked building beside a pump, the computer itself is somehow inside the building. If it has a public root, it isn't. It is standing on the internet, and the internet is now looking back.